But okay, so I will talk about vector embeddings. And, first of all, what's a vector anyway? It kind of sounds a bit scary and mathy, but like one of my goals today is to convince you that there's really nothing scary going on. So, you're probably all familiar with tabular data. So, you could have a data set like this where for each patient you have a row, you write down how old they are, what their BMI is, and whether they have cardiovascular disease. Well, like we could also write it down like this. Like, why would we? Well, just different notation. And this is like, what mathematicians will call a vector. But there's sort of nothing spooky going on. So like, we just put the age in one location and the BMI in another location. Another way to think about a vector is like, we could think about a 2D like coordinate system. And we could then like, go to BMI 33 and age 29 and put a point there. And you could think about the vector as this point, or you could also think about the vector as like an arrow going from the origin. And again, sort of like it's all the same information, what you used to like sort of looking in Excel. But like, this is like what we will call a vector. We could do the same for other patients and sort of like write that down. But the important takeaway here is that like a vector, it's just a list of numbers, a way to store information. There's nothing sort of like scary going on. And now, like, like in health data, we are often interested in predicting things. So we could like, ask what is like, the risk of cardiovascular disease given someone's age and BMI. And the way to do it is that we could like fit a linear model, just a regression model, where we have an intercept and then a coefficient for age and BMI that tells us sort of how much do they contribute to someone's risk of cardiovascular disease. And because here we're talking about a binary outcome, we want the probability. We just put it through this function that makes sure that whatever we put in, we get something between 0 and 1 out, so like a valid probability. And like this is a bit of a tangent. Feel free to sort of jump in if I'm going a bit too fast or a bit too slow. But you can also think about a linear model as just a direction in feature space. So feature space, like, we could like have this BMI H plot where we put each point. And then the weights of our linear model just tell us in which direction like the risk is increasing, and also how large the contribution relative like of age and BMI is. So like, in the case where BMI didn't contribute at all, we might be a bit like here. So there's like 0 contribution from BMI, and we just move along like, the older people are, the higher the risk. And then, we could also kind of, after we fit the model, we could then also kind of color in the space according to how high the risk of cardiovascular disease is, depending on your age and BMI. So, again, it's kind of like just a direction in the space. Of course, in 2 dimensions, it's easier to think about, but it's the same in more dimensions. So, with this kind of tabular data, we have numbers, so we can just fit a regression model. If we have images, well, I'm not sure sort of like, how we can do math on kind of like eyes. So we can't just fit a coefficient to someone's eye. And this is kind of where the idea of foundation models and vector embeddings comes in. So we could just take an image, put it through like a foundation model, and we get what's called a vector embedding. Again, a vector is just a list of numbers. So like, on the left we have a vector, on the right we have a vector. And again, we can write the vector down in this mathy looking notation. We can write the vector down in something you could open in Excel. It's all the same information. And then we could just like, fit a regression there. A brief tangent, high dimensional spaces are a bit weird. So like, there's sort of mathy things that you could say, but I don't find them too intuitive. So I will say something that isn't actually true, but hopefully communicates this, a good idea. So like, in 1 dimension, like, 1 meter, if we scale it up by a factor of 3, we have 3 meters. In 2 dimensions, if we have a square meter and we scale it up by a factor of 3, we now have 9 square meters. And in 3 dimensions, if we scale it up by a factor of 3, we have 27 cubic meters. So kind of like, as a child and even as an adult, kind of like volumes can be surprisingly large. If you sort of ask yourself how many liters fit into a bathtub, quite a large number, even though a bathtub isn't actually that large. Now, of course, like different dimensions are incomparable. Like, 10 square meters is not larger than a meter. 10 square meters is a completely different thing than a meter. But this is kind of like, maybe to get intuition. And there's also this famous quote about like, to think about a 14-dimensional space, you just visualize a 3-dimensional space and just convince yourself that you're really thinking in 14 dimension. But the important thing is that like 1,024 dimensions is not just like, 1,000 times larger than 1 dimension. It's like a billion times larger in terms of like how much information you can fit and how many degrees of freedom you have. Yeah, And I think this is basically the same. So here we also have like the quote of going from 13 dimensions to 14 dimensions creates as much complexity as going from 2D to 3D. So you can think about, you do that 1,000 times, you have quite a lot of complexity. Another thing to realize is that, I'm sure at this point, everyone has heard about deep learning models. Personally, I'm skeptical whether they will catch on, but they've been around for a minute. Yeah, you have convolutional networks, but you also have vision transformers. And what I'm not sure if everyone realizes, for instance, in code, we can inspect what is this model actually made of. And we find, in the case of a convolutional neural network, we find lots of convolutional layers and normalization layers and activations and so on, which you would expect. But then if you look at the very end of the model, you find a linear layer. So it's just a linear model. So you have all your layers and then prediction. But if we zoom in at the very end of our network, kind of like after the penultimate layer, we get a vector embedding, and then we just have a linear model, like a linear layer, that converts this vector embedding into, for instance, the risk of cardiovascular disease. If you're not sure what a linear model is, I think most of us have sort of had some stats education, but after my stats education in my undergrad, I swore to myself to never touch statistics or programming again. So some of us might be very comfortable with the notion, some of us less so. But either way, don't worry. Like, the most important things to take away is that linear models are very easy to train. Like, they're very quick to train, and they're also tiny, so we can store them very easily. And again, a linear model is just like, in the case of tabular data, you would have one number for the intercept, one number for how much age affects your risk, and one number for how much BMI affects your risk. So something quite small. And so now we know, like, a deep learning model just gives us a vector embedding of the image. And a quite natural question that arises from that is, like, instead of having a deep learning model for each like kind of specific task, what if we could have a deep learning model that provides like a useful vector embedding that we can use for lots of different tasks? And that's just the idea of foundation models. So my brilliant colleagues here at Moorfields at UCL have a very famous one for retinal images, for instance. And the idea is just, you take your image, you put it through your foundation model, and you get a vector that describes what's going on in the image. You could also open it in Excel. The vectors, nothing like mythical. We can, they're just numbers that we can look at. And I think one important thing to think about is, so tabular data and vector embeddings, we can store and open both of them in a spreadsheet. So they're kind of similar, and they're both meaningful descriptors of something. So the first describes someone's kind of like systemic health. The second describes sort of what's going on in the image. But an important difference is that for kind of standard tabular data, we know what each column means. Whereas for vector embeddings, they're still meaningful, but they're kind of abstracts. So there's a lot of information, but we can't just look at the vector embeddings and sort of understand them as a human. One way to think about it, and like especially for the clinicians in the audience, this might be a bit weird, but please, like, I'd be really curious to hear whether it's easy to understand or whether I need to explain it better. But if we go back to representing a like sort of the vectors for different patients in this coordinate system. So like, this person has a BMI of whatever we have here and an age of whatever we have here and so on. So each of these we have like, a BMI and an age, then using the color and marker to say whether they have cardiovascular disease. So this is just like, it's just vectors of patients. Now imagine if for whatever ungodly reason, we kind of like took all of this data and we just rotated it. And like, now we have like two new dimensions. So we have like an abstract dimension 1 and an abstract dimension 2. If you sort of look carefully, we still have exactly the same information. And if we knew kind of like, which direction age and which direction BMI is, we could sort of like read off age or BMI exactly as easily as before. But in these new two dimensions, dimension 1 and dimension 2, well, now they both are kind of like some part, like, if you go along dimension 1, age increases and BMI increases, and the same is true for dimension 2. So kind of like now we're in a weird state where dimension 1 and dimension 2 are kind of abstract, and we can't directly interpret them without sort of like, trying to understand our data and figuring out, and then sort of like we could rotate it back and read off age and BMI again. But if you just got this data with dimension 1 and dimension 2, in some sense, you would have exactly the same information as you have on the left. So like, both of these like store exactly the same information. It's just that in the case on the right, it's not directly humanly interpretable. And we sort of like would need to do some work to understand what dimension 1 and dimension 2 mean concretely. And you could like, so I've shown it here with rotation. You could also think about it with stretching and kind of like squashing the space. I'd be curious if anyone can tell me whether this sounds like complete nonsense or whether it's solved. makes any sense at all? Is it trivial? Does anyone want to chime in?
I just capital. I think I can kind of see where you're going. Are you going to go on to image augmentation from this, or am I on the wrong side?
Sorry, I think your audio is a little bit muffled. So I got some of that, but maybe could you put it in the chat so I can make sure
Sure.
I got it properly. Sorry about that. Although I'm not sure if I can see the chat.
Justin, what would you say if just again for a clinician who doesn't have a deep understanding of some of these things, what is the point? Can you clarify the point that you're making by rotating the image by 45 degrees or whatever amount that you did?
Yeah, so kind of like your question is, why would you want to do this, right? And thanks for putting it in the chat. So it's a bit about data augmentation. And to Tom's point, if I'm making sense, you're probably misunderstanding me. And if you understood me better, like you would know that I'm not making sense. But so it's not quite data augmentation. We sometimes rotate images when we train models and so on. And to Michael's question, why would you want to do this? Well, of course, you would never want to do it. Like, you have a data set that you can understand. You wouldn't want to like then turn it into something you can't understand. The point that I'm trying to explain here is like, so both of these are meaningful descriptors, but whereas in the first case, we can directly read off what each dimension means. In the second case, we really can't read that off. So like, for instance, in the image, images have different brightness, and like, there's like an optic disc, and there's the vessels, and maybe there's some pathology. So there's lots of things going on in the image. And all of that information, or at least like, some information that are model extracted, is stored in these numbers. But we don't know that dimension 3 is just how bright the image is, and dimension 2 is whether it's a left or right eye. So it's kind of like, in this case, like each of these dimensions capture information, but we don't understand what the information is easily. So this is kind of like, if you, instead of having this data set on the left, you have the data set on the right. So the data set on the right captures exactly the same information. But if you, like, if someone sort of like dropped that data set into your lab and you didn't know that, like, one axis is BMI, one axis is age, in some sense, you have the same information about each patient as before. And like, you could also predict cardiovascular disease just as well as from the original data, but you sort of don't understand what the dimensions mean. So this is kind of like trying to illustrate the point. Like, so vector embeddings are a bit more like this case on the right. So there's meaningful information in them, but we don't understand what it means. Whereas like tabular data, there's meaningful information in them, but we understand what it means. So this is kind of like what I was trying to explain.
Very helpful.
Let me see what's. Yeah, great. So Paul has an interesting question about whether there's any guarantees about what foundation models do. And kind of like, by tangential, do you mean whether they are orthogonal or correlated?
Correct.
Yeah, that's a good question. So this is also something it's maybe a bit more advanced, so some people don't be too fussed about that. But it's kind of, so first of all, we're just hoping that like with self-supervised learning, we end up extracting useful information. And there's also a bit of a like no free lunch theorem, and that like what information you want to extract from the image depends on what you want to do. And in some cases, there's information that you would like to ignore. So for instance, image quality, for a lot of tasks that we want to do with retinal images, we actually would like a model that's kind of invariant to whether the image is a slightly higher quality, slightly worse quality. We want to know what's actually going on with the retina. But of course, if we were scoring image quality, so if we had a model that sort of automatically told us, is it a good or bad quality image, we want that information. So kind of what information you want your vector to capture also really depends on the downstream task. And then this is also like something that like maybe the self illustrate. You might think that a good vector would kind of like each dimension would give you a different piece of information. But with this rotation example, you can see that it's a two-dimensional data set, and we have like sort of 2 dimensions of information. So in that sense, we're using both dimensions efficiently. But on the left, there would be a loose correlation. On the right, there would be probably quite a strong correlation, because now each dimension is picking up both BMI and age at the same time. So what you're asking is more, so even if you have a foundation, like, a data set of vector embeddings, you might find that different dimensions are highly correlated, but that doesn't mean that there is redundancy in the representation. What you're actually interested in is what's called the rank of the matrix. So kind of like, loosely, if you did PCA, like how many dimensions do you actually need to explain virtually all of the variance in your data set? So hopefully that that made sense. Let me look at what Tom was saying, or Tom, if you if you can speak, feel free to just jump in.
So I was just typing when you were explaining before, just in a nice visual way of understanding what the embeddings are doing is you can see a lot of tutorials online where people just walk along the embedding space, don't they? And they'll change like embedding 1 to a different number or something, and then you reconstruct the image and you can see that embedding therefore represented a certain part of the image. You know, when you're talking about like things with different colors and stuff, you can visually see that when you look at the tutorials and things online, can't you?
Yeah, so for generative models, you can do that. One interesting thing for generative models is that, like often, like either by chance or we enforce it explicitly, there's like some kind of Gaussian distribution to the dimensions, and actually, which is something really tangentially related, but quite cool if you hadn't thought about it. A high-dimensional Gaussian is actually less than the Gaussians that you're familiar with in like 1 dimensions or 2 dimensions. It's actually more like a very thin soap bubble. And like, you know, the intuitive explanation is if you have like, you know, 1,000 times like a 1,000-dimensional space and you sample from a Gaussian 1,000 times, you will basically be guaranteed to have at least a few outliers. So you will never be in the center. So when you do these interpolations between different images, actually you don't want to go straight. You want to kind of like go in a curved way to account for the structure of what people will call the latent space. In terms of like, so that's possible for generative like models, and that's quite cool. For these kind of like unsupervised models, which we would typically use, it's a little bit harder. We could generate conditioned on the vectors, but then we're sort of not guaranteed that the generative model doesn't ignore or invent information that isn't in the original vector. And like, you know, there's lots of different ways that people try to sort of do interpretability on models. Yeah. So why would we use vector embeddings? Well, one reason is that they're efficient. So a lot of people think we need like, you know, some fancy data center to do anything related to AI. If you want to buy me a fancy data center, I would never say no, but actually we don't need it. So one example, something like we've worked on recently is like, you could run a foundation model on a phone. So this is a slightly smaller foundation model that I call red, brown, green, but you could run it on a regular smartphone, and it does roughly 1 image per second. So, you know, if you had a data set of 10,000 images, it would take you about 3 hours. And that's on a phone, of course. On a laptop, you could do it even faster. And in a data center, you could do it even faster yet. But really, these things are quite efficient. So as an example, like there's 2 really cool data sets on Physionet called BRSet and mobile BRSet by a colleague of Michael and mine. And this year for ARVO, one thing we submitted is showing that, you know, sort of with red, from green, we can fit a model to BRSet and evaluate it on mobile BRSet and get like, you know, reasonable performance. But the most exciting things is like on a workstation computer, by which I mean my low-end gaming computer from a few years ago that I have under my desk. It takes like a few seconds, and even on the phone, it takes a few minutes to kind of process all that data. So I'm not sure how interesting this is to people, but here's just an example of me running it on my phone, which is like I bought it for roughly 300 euros like 3 or 4 years ago. And you can kind of see like, you know, we can put an image through it and like a good performance. Yeah, Robert, that's an excellent question. So in like, I think you probably looked at the preprint that I put out. Non-retinal foundation models perform surprisingly well. There's a slight uplift, but it's quite marginal. So there's like it's always good to have these baselines. But yeah, so we can run it on the phone. So this was like, you know, for disease detection. Another use case that like, you know, maybe to give a flavor of vector embeddings allow us to do things that maybe are non-standard and kind of interesting. Suppose you had like, you know, a few images and a data set of more images, and you wanted to ask which images in your data set are similar to these like, you know, images that you're interested in. And like, you know, traditionally, this would probably be quite laborious. You would sort of have to manually sift through them and say, which ones look similar to me. But one thing we can do is we can compute the vector embedding for each image and then find the images with the closest vector embedding. So for instance, in this case, these images on the right, they're not the same images, but they're images where the vector embedding is quite similar to the query image. So here's a few more examples of very similar images. Like, you know, I'll give you some time to look over them. Not all of them look super similar, but in general, there's some similarity. And if anyone, especially people that actually know anything about the eye and retinal imaging have any insights, I would love to hear them. But then also just to sort of sanity check, it's not that all these images look the same. So I've also given you some very dissimilar pairs where we can see, like, I mean, it's mainly this image is very dissimilar to all the other images. And then also some images of middling similarity to kind of convince you that here all these images kind of look similar to each other, but it's not because it's a data set where all images look very similar to each other. Some images genuinely do look different from each other. So I hope you kind of took away that vectors are just a list of numbers. Vector embeddings provide a meaningful description of an image, even if even if it's not humanly interpretable, and we can easily adapt them for various downstream tasks. So I have a second application of something that I'm currently working on, but maybe like a brief pause before this. Does anyone have any questions on what we've covered thus far?
Justin, thank you for that. I was just wondering, do you know if have any of you guys experimented with reducing the the size of the embedding space that you used in the master autoencoder in RetFound? Because in like conventional, so like in our group, we just use like conventional autoencoders to represent images before for like genetic analysis and stuff. And even when you encode images with 256 or 128 embeddings, you still have quite a lot of redundant ones, even when it's that small retinal images. There are a bunch of them that just don't seem to correlate with anything and don't seem to represent much interesting in the image. So I'm just thinking, when you've got 1,028 of them, presumably there's a lot of redundant embeddings in there. I'm just wondering if that's something that I know that's the implementation from Meta that was done originally, but I'm just wondering if that's something that any of you guys have played with. Did you manage to get any smaller? Does that affect performance, etc.?
Yeah, that's a great question. So, okay, so a few thoughts. First is like, even if some dimensions of your embedding space don't seem to correlate with anything, that doesn't mean that they're not meaningful, because it can be hard to find out what they mean, and also because sort of things don't have to be aligned. So it could be that one dimension isolation doesn't have any clear meaning, but taken in combination with other dimensions that kind of now means something. And then the second thing is there's something that I've kind of glossed over, but for instance, for this app, I'm using something called RedFound Green. So it's currently still under review, but there's a preprint on arXiv. And this is a model that uses a much smaller vision transformer and was trained slightly differently. So here the representations are only 384 dimensional. So kind of like, 2.6 times less space, and the model runs much faster. And I think kind of like there's often this idea that we need larger models, but actually, like, I think we want models that kind of more densely and more meaningfully like pack information into the vectors. So kind of like if we could have a vector that's just 60 dimensions, but it captures everything we would ever be interested in ophthalmology, I think that'd be great. So yeah, so there are smaller models, and I think both kind of like having smaller, more efficient models, and also having models where really the representation is like has a higher quality is very important. So you can probably find the preprint on arXiv, and the model is already available. So if you have a chance to take a look, please do let me know.
Thank you.
I had a really quick question, Justin. Let's
Yeah.
say you use two foundation models, two ways to train them. One's a master autoencoder, one's the Dino V2. Could you find one or a set of vector embeddings that are extracting the same things? So like you said, one that has got the optic disc using one method and the same thing has come out from another model, such that this is a base feature that seems to be important for maybe both of those tasks. Of course, the pretext task is a bit different. And the second very quick thing I noticed is that the similarity thing that you showed seemed to not care about laterality, which is that similar or not similar? So it's kind of this idea of what is being extracted, and is there something that should be extracted every time for a given input and output?
Yes, so those are excellent questions. The first question touches on quite a lot of different things, and namely that is like, so we have the question of interpretability, and related to that, there's like something that people have looked at a lot, kind of like under the umbrella of latent space disentanglement. So like vector embeddings, they're what's called in a latent space. A latent space just means that none of the dimensions mean anything physical. So kind of like, for looking into what you're describing, we would first need to understand both of the embedding spaces to find out, do they, for instance, represent something related to the disk, and then sort of like see how similar that is. there's like, I think, a recent literature on something called structured autoencoders for this kind of thing. But there's also then more recent literature that suggests that if you take the same model and the same data and you fit the structured autoencoder a few times, they will give you very different like sort of explanations of your embedding space. So this kind of like, understanding what vectors mean often has like a flavor of like reading tea leaves. So it's a bit tricky. And the second question, I think that's also kind of like something I've thought about a lot is like, what do we want the vectors to represent? So for instance, we also have like an element of like whether the image is like, slightly cropped and how much like, sort of like space we have around the image. And, if you wanted to have a classifier for cropped image versus non-cropped image, of course, you want to retain that information. So like, it really depends on the task, and same with quality. Like, do you want a blurry image that like, shows proliferative DR to be very similar to a non-blurry image that shows proliferative DR, or do you want it to be similar to a blurry image that doesn't show like DR, right? Like, so there's lots of different things that we could or could not care about. But I think one direction that I'm interested in is trying to train models in a way that we have a better understanding of like what the vector space means, so that we're not just like hoping for the best, and also sort of thinking hard about what kind of like invariances do we want to inject in our models. So for instance, in my opinion, while sometimes we care about laterality, like, if you have a big data set and you want to sort of analyze left and right eyes of patients separately or something, you might want to have a classifier that tells you, is it a left or right eye? But for a lot of cases, actually, we don't want like sort of the model to care about that, and we want to sort of focus on what's going on with the eye and so on. So that's something that I've been thinking about. And also to Tom's question, I should also say I've done a little bit of work looking at the rank of these embedding matrices. And for instance, for red found green, but it's sort of, I need to look into it further, how to like sort of like to understand it a bit deeper. But like, for instance, if you do PCA with embeddings from red found and embeddings from red found green, it seems that like red found green is much closer to full rank. So kind of like all 384 dimensions actually capture something different, or at least most of them. Whereas like for red found, it's more like 600. So kind of like 40% of the embedding space is a bit redundant. So it's something that I would also be interested in to look into a bit further. But I think sort of like one good direction for training these models is not to just scale them up and hope that they magically perform better, but it's kind of like actually having smaller embedding spaces that are more meaningful, where we sort of really make sure that we have a dense, meaningful representation of what we're doing. Great. Any